What does it actually mean to prove a theorem with a computer? It is not just checking a numerical calculation. It is not just running a test on a handful of inputs. It is taking a statement like, every continuous function on a closed interval attains its maximum, and having a machine verify, line by line, that your proof is sound. Modern proof assistants like Lean, Agda, and Rock, formerly known as CoC, can do this. And underneath all of them sits a single unifying idea: the Curry-Howard correspondence. The idea has a very simple statement. Every proposition can be encoded as a type, and every proof of that proposition is a term, a program of that type. Logical connectives line up exactly with the type formers programmers already use. A and B is the product type A cross B. A proof is a pair of a proof of A and a proof of B. A implies B is the function type A to B. To prove the implication is to write a function from proofs of A to proofs of B. The consequence follows directly. A program that decides whether a term has a given type, daddy, is also a program that decides whether a proof proves a given proposition. That is the entire reason proof assistants work. To make the correspondence sharp enough for real mathematics, we need a type system rich enough to express the propositions we care about. That type system is the calculus of constructions. CoC, written Lambda-C. It is the minimal type system that can do the job, and the common ancestor of the type theories that Lean, Agda, and Rock actually use. We will get there by climbing. We start at the simplest typed lambda calculus, and the one most programmers already know. Add one new feature at a time, and at the top, with every feature switched on at once, we land on CoC. If you have written an anonymous function, a lambda, in any modern language, you have already used a typed lambda calculus. The most basic one is called the simply typed lambda calculus, STLC for short, written lambda arrow. STLC has two ingredients: a type-forming rule that builds function types A to B, and a term-forming rule, lambda abstraction, that builds function values. This is the identity function on type A. It takes an argument x of type A and returns x. Its type is A to A. The typing rules are short. To form a lambda, you assume the input has some type and check the body. To apply a function, the argument's type must match the function's input type. That is the entire simply typed lambda calculus. Every term in STLC is just a value depending on other values. Or in our lambda cube vocabulary later, terms depending on terms. STLC can express a lot, but it cannot express every function we actually want to write. Consider the identity again. This definition works for any type A. Integers, booleans, lists, anything. But in STLC, we have to fix A up front. So in practice, we end up with a separate identity per type. One for int, one for bool, one for every type we will ever use. That is unsatisfying. We want one identity that works for every type. To get it, terms have to depend on more than just other terms. They have to depend on types. That is the first new axis. System F, also called lambda 2, adds a second kind of lambda. Capital Lambda takes a type sequence as its input. The type of this polymorphic identity uses a universal quantifier over types. To use it, you apply it to a concrete type first, then to a value. This is parametric polymorphism. It is exactly what you write in a Haskell-type signature as for all A to A. Or in Rust fnid of t, taking x of t to t. In Lean, the same idea looks like this. The curly braces make alpha an implicit argument that Lean will infer at the call site. But underneath it is exactly the polymorphic lambda from System F. So far, types have been opaque atoms, but often we want to build new types from old ones using a function, a type-level function. Pair is itself a function. Applied to int and bool, it produces the type of integer Boolean pairs. To handle this honestly, type theory introduces kinds. A kind is a type of types. Ordinary types like int and bool live at kind star. A type-level function like pair lives at kind star to star to star. The lambda calculus that lets you abstract over types at the type level, write lambda expressions whose results are types, is called lambda omega. This is the second new axis. Combined with System F, it lets you write generic containers parameterized by element types, just like pair. So far, our types can depend on other types, and our terms can depend on both other terms and on types. There's one combination we have not seen yet, the most powerful one, and the one that turns this whole machine into something that can check proofs. Types that depend on values. Here's the canonical example. A vector of length n holding values of type A. The number n is a runtime value. It is a term, not a type. So vec-A3ers and vec-A4 are different types. The type depends on the value. That lets us write a function whose return type encodes its behavior. The type literally says, appending a vector of length n and a vector of length m yields a vector of length n plus m. If you implement this and get the arithmetic wrong, the type checker rejects it before the program ever runs. To express types that mention values, we generalize the function arrow a to b into a dependent product tout, written with a capital Pi. Read it as for every x of type A, a value of type b of x. The body b is a type that may mention x. The ordinary function arrow is just the special case where b does not mention x. The lambda calculus extended with dependent function types is called lambda pi, also known as the Edinburgh Logical Framework, LF. Here is the payoff we hinted at in the beginning. Once types can mention values, propositions become types. The proposition for every natural number n plus 0 equals n is literally a type. And a proof of that proposition is just a term of that type. A function that given any n produces evidence that n plus 0 equals n. That is the Curry-Howard correspondence made concrete. Writing a proof is writing a program. That is the entire reason proof assistants are built on dependent type theory. Step back. We have collected 3 new axes on top of plain STLC. Each axis is independent. You can switch any subset on and the result is still a well-defined typed lambda calculus. 3 independent on-off switches give us a cube of 8 systems. The lambda cube, classified by Henk Barendregt in 1991. STLC sits at the corner where every switch is off. Each switch flipped on corresponds to moving along one edge of the cube. What sits at the corner opposite STLC with every switch on? The calculus of constructions, lambda C, is the top corner of the cube. It was introduced by Thierry Coquand and Girard Huet in 1988. Terms can depend on terms. Terms can depend on types. Types can depend on types. Types can depend on terms. Every kind of dependency the lambda cube allows is allowed in CoC at once. And CoC unifies them all under a single binder. Every dependency, value level, or type level is just capital Pi. Every binder is just lambda. There's no separate big lambda for types. Types and terms live in one syntactic universe. In Lean, this is exactly what you write. And Lean does not care whether alpha is a type or a value. The same machinery types checks both. That uniformity is exactly what CoC buys you. You now know the engine. STLC, System F, type operators, dependent types. 4 corners of a cube whose top vertex is CoC, the type theory that lets a proposition and its proof be written down in the same language. But CoC by itself is not quite enough to do real mathematics. 2 ingredients are still missing. CoC actually has 2 universes, a universe of propositions prop and a universe of types type. Prop sits inside type, but type itself has no type. Try to write type:type. And Girard's paradox fires off, the type-theoretic cousin of Russell's paradox. The theory becomes inconsistent. The fix is to stratify type into a hierarchy of universes. Type 0 sits inside type 1, type 1 inside type 2, and so on. No type ever contains itself. CoC extended with this hierarchy is called CC omega. Concrete types like gnat live at the bottom. The type of gnat is type 0. The type of type 0 is type 1. That is what kills the paradox. The other missing piece is a primitive for building new data types. The natural numbers, lists, trees, by listing their constructors. In Lean, the natural numbers take 3 lines. 2 constructors fully describe the natural numbers, and each constructor is a typed function into the new type. From these signatures alone, the kernel derives both pattern matching and the induction principle for free. You write down the constructors, and every function by cases and every proof by induction on the type follows automatically. No extra axioms, no separate definitions. CoC plus univers plus inductive types is the calculus of inductive constructions. CIC is the foundation of ROC, and Lean 4 uses a close variant. Achte's Martin Löf type theory follows a slightly different lineage but makes the same 2 moves. In the next video, we'll dig deeper into inductive types, how pattern matching and induction principles are derived, and what makes them a faithful primitive for mathematics. Thanks for watching.